Okay, in this video I'm going to talk about Brocard angles. So this is basically a continuation of the previous video about Brocard points of a triangle. So recall that we proved that in any triangle there exist two points. So one of them is the first Brocard point and another is the second Brocard point. So they are defined by the property that so these three angles are equal to each other. So this is the first Brocard point, ABC, and the second Brocard point is, it's better to draw it on a separate picture. The second Brocard point is that these three angles are equal to each other. Oh, no. Yeah, these triangles. So they exist and they're unique. So like the point P with the property that these triangles are equal to each other, it exists and it's unique. So that's what I proved in the previous video. So now so the question is what are these angles? So this angle for the first Brocard point, these three equal angles, so let's denote it by phi1, and the angle for the second Brocard point, let's denote it by phi2. And so it turns out like a very interesting property that they're equal to each other. So phi1, it turns out that it is equal to phi2. And we can calculate it using the angles of the triangle. So let's write it as a theorem. So let's write theorem that phi1 is equal to phi2 and is equal let's write it this way. So the cotangent of phi1 is equal to cotangent of phi2 and is equal to the sum of the cotangents of the angles of the triangle. So let's denote the angles of the triangle. So ABC, let's denote them by alpha, beta, and gamma. So this is equal to cotangent alpha plus cotangent beta plus cotangent gamma, and in particular so like we can write it as a corollary. As a corollary, phi1 is equal to phi2. So because like we explicitly calculate both phi1 and phi2, like the cotangent of phi1 and phi2, and it turns out that both of them are equal to this expression, and from this it follows that phi1 is equal to phi2. And so like when I was preparing for this video, like I found on the internet some claims that allegedly like it's possible to prove directly the equality of these two angles, like with some easy argument, but like they didn't give the argument, and like I thought about it, and like I don't see any easy argument that would prove this. So like maybe I'm missing something obvious, but like to me it seems that like I don't see a simple argument that would prove directly that these two angles are equal to each other. So like if somebody knows this, like you can write in the comments. Okay, so we will prove the equality of these angles using by establishing the this expression for the cotangent of both of these angles. So first, proof. So first we notice that the case of phi1 and phi2 is similar. So like if we prove this, the cotangent of phi1 is equal to this expression, then the case of phi2 would be, because you see like it's kind of, the picture is kind of symmetrical. So all we have to do is basically change the order of the points A, B, and C. So like, because if instead of the triangle ABC we consider the triangle ACB, then the first Brocard point becomes the second Brocard point and vice versa. So they exchange places. And so because of that, like if we prove the expression for phi1, and the expression is symmetrical by alpha, beta, and gamma, then by using a similar proof for symmetrical triangle, we automatically establish the expression for phi2. So so let's draw picture. So now we'll prove for phi1. So we will prove that the cotangent of phi1 is equal to this expression. So we have this triangle. We have this point P such that this angle is equal to this angle and is equal to this angle. And like in the previous video when I proved the existence of Brocard points, existence and uniqueness, so we construct the circles. So basically, like I proved in the previous video, that the circumcircles of the triangles, so of the triangles APB, BPC, and CPA, so the circumcircles are tangent. Well, we don't even need to prove it, like it's kind of obvious. So this circumcircle, it is tangent to the line BC, because this angle is equal to this angle, right? So BAP is the angle BAP is equal to the angle PBC. So this means this is exactly the angle between a chord and the tangent, and so it's equal to the angle subtending the same arc. So if we have the equality, like it's a well-known property that if we have the equality of these angles, then BC is a tangent. And similarly, when we draw this circle, it is tangent to the line AC, and when we draw the third circle, it is tangent to the line AB. Yeah, so now what we do is we extend the segment CP to the second intersection with this circle. So we obtain this point so let's denote it something. Let's denote it K. And we also consider the diameter of this circle. So there is a center here and the diameter from point B. So consider this point M. Right? So yeah, so observe, so now we connect this and this and this. So now observe that this angle is also equal to phi1, because like to all three angles, all these three, to the Brocard angle. So yeah, by the way, I forget to say at the beginning that the angles phi1 and phi2, they're called Brocard angles. So the points are called Brocard points of a triangle, and the angles phi1 and phi2 are called the Brocard angles. Okay, so this angle, because it subtends, so it is an inscribed angle in this circle, and it subtends the arc BP, right? And the arc BP, so another angle that subtends the same arc is this angle BAP, right? So these are two inscribed angles subtending the same arc, therefore they are equal to each other. So therefore this angle is equal to phi1. But now, since so let's write this. So so I said that the angle BKP is equal to the angle BAP, because they subtend the same arc, and this is equal to phi1. And now phi1 is also equal to the angle ACP. So ACP and BKP, so these two angles, because of the equality of these two angles, we conclude that the line AC is parallel to the line KB, right? Because these are the two angles between a common line intersecting both of them, KC, and these two lines. Because they're equal, it implies that AC is parallel to KB. Okay, now because of the because MB is a diameter, we have this angle is a right angle, right? Because an inscribed angle subtending half of a circle is 90 degrees. So now because it is a right angle, so let's write this. So MK is perpendicular to KB, but because AC is parallel to KB, so from this we conclude that MK is also perpendicular to AC, is perpendicular to a parallel line, to a line parallel to which it is perpendicular, right? So if we extend it here, let's denote this point by L. So this is a right angle as well, because of the parallel lines, right? So now we consider the triangle, like this large triangle. Let me highlight it with blue. This large triangle, it is a right triangle, right? And one of the angles is phi1, exactly. So then the cotangent of phi1 is equal to the ratio of the sides of this right triangle. So it's equal to LC It's basically by definition of cotangent. So LC over KL. All right. So now we divide LC into 3 parts. So we also consider the altitude here from B. So this is an altitude, and this point is HB. And so now we have KBHBL. It's a rectangle, because like the two KB is parallel to LC, and we have everywhere the right angles, so it's a rectangle. So now we divide LC into 3 parts. So LC is equal to CHB plus plus HBA plus AL, right? So we divide it into 3 segments. So CL, we divide it into CHB, HBA, and AL. In the denominator we keep KL. And it is also like, because it's a rectangle, like KBHBL is a rectangle, KL is also equal to BHB. We will use it. So now we rewrite it as CHB over KL plus HBA over KL plus AL over KL, right? So now here we use that. Let's remove it here and write it here. So so CHB over KL. So here we replace KL with BHB, and this as well. So let's rewrite this. So this would be equal to CHB over BHB plus HBA over BHB plus AL over KL. This we keep as this for now. So now let's look at the picture. So what is CHB over BHB? So CHB, so let me highlight it with green. So CHB over BHB. So these are the 2 sides in a right triangle, right? So the ratio of these 2 sides is exactly the cotangent of this angle, right? Of angle C in the triangle, which is gamma. So this ratio, the first fraction, is exactly cotangent of gamma. Now, what is HBA over BHB? So let me highlight it with blue, with yellow now. So AHB, this over this. So this is again a ratio of 2 sides in a right triangle, and it is exactly the cotangent of this angle, which is angle alpha in the entire triangle ABC. So plus cotangent alpha. Now the third one, so AL over KL. So So this is this triangle, right? AL, I showed it, highlighted it with red on the picture. So AL over KL. So this is the cotangent of this angle. But so what is this angle? So actually, because of the parallel lines, so LC, LC is parallel to KB, right? So this angle is equal to this angle. So let's write it here. So let's write it separately. So AL over KL is equal to cotangent of the angle LAK, which is equal to cotangent of the angle AKB, because of the parallel lines, these two angles are simply equal. AKB. So now AKB, it's an inscribed angle that subtends the arc BA in this circle, right? So, but we have here the tangent, and so the angle between the tangent and the chord subtending the same arc is this angle ABC, because it's an angle between a tangent. BC is tangent to the circle, and AB is a chord, and it subtends the same arc AB, right? So this is the angle between the tangent and the chord is equal to the inscribed angle subtending the same arc. So this is equal to cotangent of the angle ABC, and ABC is exactly beta. We denote the angles of the triangle as alpha, beta, gamma, right? So ABC is the angle in the original triangle, so we denote it as beta. So look here, so we expressed AL over KL, so exactly this expression as a cotangent of beta. So here we add cotangent beta, and this is exactly what we need. So we started with cotangent phi1 and arrived at cotangent, well, gamma, alpha, and beta. Like we can even rewrite it as cotangent alpha plus cotangent beta plus cotangent gamma to have the same order, but it doesn't matter. Yeah, so this is the same as the expression that we needed to prove here. Yeah, so this basically concludes the proof for phi1, and as I said, the proof for phi2 is similar. So we like repeat the same argument for phi2, and arrive at the same expression. Yeah, so this concludes the proof.